This is a Linux kernel tutorial with a hands-on experience. You will have the compilation steps to compile the Linux kernel, and then you will be able to debug using kprobe, where you can probe the Linux kernel functions, and you can also see examples about tracefs, and you can also debug the sockets with Netlink sockets. So how to do, and we have also taken two examples of SRv6 static and subnet. Today we will see how to compile the Linux kernel. So I already have a kernel which is 5.15.49. So I am going to take the latest kernel and compile. I have already compiled. I will show you the steps how to do it. So you have to go to kernel.org and then I will take the latest. This is 19.0. So here you put a right click and do a copy link address. You have to take this address. You do a copy link address, you will get, then you put get wget-c and paste it. So if you do this, you will get a source code. So I have got the source code. I have done this step already. So this is a source code. Then you have to do tar-xvf of that file. So that also I have already done. This is the step. tar-xvf linux.tar. If you do this, it will create this folder. If you go inside this is the source code. This is the Linux source code. So we are going to compile. So for compiling, first step you need to know is install the dependencies. So apt-get install git. So all these you should install. It is already installed in my system. If not, it will ask for a question. I will take some time to compile. Install. Then you have to do this command. What this command does is, it will copy. 1 minute, I will just show. I have already done, so it will overwrite it. I will just show you the. So this is what it will take. It will take from boot config this file and it will copy it in this current folder. So I have already done. So I am not doing it again. Then you should do menu old config. Make old config. This if you run, it will take the default configs and it will copy. So this is the command you have to give. This also I have already run. So after this you should do make menu config. If you do make menu config, it will also show, see, it will come like this. It will take some time and it will give menus. You can select whatever you want and then you have to do a make. So this is what. So you can select any options you want, virtualization, if anything you want you can enable and you can do anything. So network support. So M shows that it is a KO module, star shows that it is a O module. So I am just doing an escape. I am not doing anything. I will say no. So not saved. So, but you should give S and come if you make changes. Then you should give a make. So this is make. So I have already compiled. So now since it is compiled, it will come up. When you give a make, you will face some issues in this particular kernel version 5.19. So this first error is this. You will get this error. So how to solve this error is, you have to create a folder like this, user local src, and then you should do apt-get install source. This means it will copy the source code to this file, user src linux. So from there we will copy this canonical start pm to our local deb. Then you remove, this command will remove that user source src, and then we have to copy this user local src bin to our source code path. Once if you do this, this error will be solved. Second error which you will face is this error. So to solve this error, you have to install dwar-waves. So this you have to do. If you install this, then you will not face this issue. The third issue which we faced is ZTD is not found. So for that you should install ZTD. Done. You have to do sudo make modules install. So this will compile all the modules and install it in this folder, lib modules. In this path it will install. This is the path in which it's going to install, because we are using this 5.19 kernel. The next step is you have to do make install. So what this will do is, this will copy. It will take a long time. I'm just saying the steps, what all it will happen. You go to boot. Here it will copy all these VMZ images. And then next step is, we have to create a initrd image. So for that, open this file etc initramfs tools initramfs.com. In this file, search for this modules. In modules, default it will be most. Most means it will add most of the file system and all the hardware drivers. So it will make the Linux heavy. So we can use deb. So it will install only the needed dependable modules. So that's how we can reduce the size of initramfs. So do that change, and then you have to do this. This is the command to update. Update initramfs -c-k this name. So this name how you can give is, first you should know which kernel you are compiling. For that you can see this name. But once it is installed, it will be installed in this modules. In this module, what name it has done, the same thing you have to give. So this name should match with this name. So once you do this, it will create this file in boot. It will create this initramfs. This one, 4. This image it will create. So once this image is created, you have to update the grub. For updating the grub, this is the command. So if you give this command, what it will do is, it will go to boot grub. It will go to this file, boot grub.cfg. You can see this name 5.19.0.rc. You have to search this here. It will put an entry here. So this is the entry. This is recovery version and this is the normal version. So it will put this entry in menu con. So while booting, you can see this and you can enter inside this. So that is the reason for installing. So once all these steps are installed, you can do a reboot. So for reboot, this is the command, sudo reboot -h now. So once giving this, I'll show you. Once you give reboot, you will get this option. In this option, you can go to advanced option and give an enter. Now you will be able to see the kernel which you have created. This 15.15 is old, 15.9 is this. So and then you can press an enter and it will go from a normal reboot. Once it boots up, we can telnet and see whether kernel is getting upgraded. System is booted now. Now we can give uname -a and check. See, it is changed. So now we are success. We have upgraded a kernel from 5.15 to 5.19. You can try the steps. Thank you. In this video today, we will try to learn how to do a kernel debugging using the kernel traces. So for that, first we need a tracefs. So this is the Linux machine which I am using. It is 6.2. So first thing is, you have to give this command mount tracefs. Trace in that grep for fs. So if it is there, then it shows that you can trace the kernels. If it is not there, you have to enable this and compile in the kernel. So this will be mounted in this path. This kernel tracing and is a tracefs file system. So this is the first thing. Only if this option is there, you can start to debug. Now we'll go to that path, this kernel tracing. So to this path. So wherever this path is mounted, to that path you have to go. These are all the different commands. Now we'll see whether tracing is enabled or not. So for that, you have to give this tracing on. This is the file. If this is 1, then means tracing is on. If it is 0, then means tracing is off. So we can try to switch off the trace. Echo 0 greater than tracing on. So now tracing is off. So you also have a command called as file called as trace. So here you can check. See here tracer is no off, so will show the actual tracing logs. So now currently it is off. Now we'll try to switch on. How to switch on? Just put 1. That's it. So now tracing is on. So what all we can trace? So for that you have to go to this path available traces. So all these things you can trace. This is hardware, this is function graph, wake up graph, function and NOP. By default it is NOP. So now today we will check how to see function graph as well as function. So where to set this options, available tracer options. So for that you have a file called as current tracer. So current tracer is NOP. That means there is no tracing enabled. No particular tracer is enabled. So we will try to enable now. For enabling it, you have to do echo. You have to give function graph and then current. All these you need root permission, only then you can do it. So now the current tracer is set to function graph. For all the outputs, you have to see this file. So see, all the traces are enabled now. So that's why you are getting like this. So anyway, we cannot debug like this. So we need to add a filter. So how to add a filter? So this is actually if you want to see this log, you can just see what are all scheduling, what all spin logs are there. So this is the current task of the kernel. Everything it is loading. So with this, we cannot see particular variable or particular function. So if you want to debug a particular function, then we have to enable the filters. So for that, first we'll see what are all the available filters. So this is the file available ftrace ftrace filters. So this is showing all function enabled. So that's why we are getting all the functions. So now we have to give a particular function here. So this is ftrace, like that graph function, everything we can do. So for now we'll check this. So what are all the available filters? So for that available filter function. You see these are all the kernel functions. So when these functions are getting hit, we will get a trace here. So today what we will try to do, we'll just try to ping with ICMP and we can check. So for ICMP itself we have all these things. So out of this we can select few. I have already selected few. So what we have to do, I am doing is echo this function I am copying to ftrace filter. So I am just appending it. We'll see after this command. So all these I am appending to this set ftrace filter. You know, if you see, it will start debugging for this one. Old things are there, so we have to disable it. We can do echo NOP current tracer and then we can enable function. So now if I give C trace, so nothing is there. So see, tracer is function graph. So now it will give all these filters. Only these functions will be traced now. If you want to add more, you can add more here. So now, since it is ping, it is easy. So I have added this. So now we will try to ping to google.com. So one packet. So now we'll see the traces. This still shows the old one. We will re-enter and we'll check. You can once try with function. Try with this function. This is showing correctly. So ICMP receive, it is getting hit. So you can see the task ID, IRQ, what is the request. And from there, it shows from IP protocol deliver RCU, we are getting to ICMP receive. So this is a working correct packet. So we'll try to send to some other IP which is in this network, but it is not reachable. So we should get an error just to see. And trace. We got this. IPv4 link failure, send push reply. So it gets some error because error I have not logged, but still it gets a failure. We are getting a failure. So this is from the software IRQ, like that's all the tasks in CPU, everything you can find it out here, and this along with the timestamp. So I think this would be useful. Now we will try to switch over to that function trace. We had this. Now we'll move to function graph, and we can. Function graph now. Now we'll do the same exercise. This is a working case. So this goes like this. And we'll do a non-working case. So here you see it says ICMP receive, and then from there it goes to ICMP send reply. So software it is similar thing, but that is with a function call. This is with a function graph from where it calls and how it goes. So this is very useful for kernel debugging. I'll just recap it. So first you have to check the mount whether tracefs is on. If not, you have to compile the kernel with that and move to the path in which it is there. In our case, it is kernel debug tracing. So usually it will be in that path only. Sometimes it is okay. Here in both the paths it is there. You can check in sorry, both the paths. So we were still now working with trace. We can also work with debug. And then the function to check whether it is on or off is this tracing on. And all the available traces you can check in this available tracer. Current tracer you can put here. The available tracer options, we have function and function graph, and these are the available filters. You can just enable this. You have to append it so that you can trace all the required functions. So this is how you can debug the kernel internals. So it is very useful if you want to understand anything in the kernel. So thanks. We'll try to understand how to use kprobe to debug the kernel. So we have taken, we'll start. This is the kernel 6.2. So to start with, and just check the mount command to check whether debugfs is installed. So it should be in this kernel debug. So to confirm this, you can go to boot and you can go to config. Since it is 6.2 kernel, you go to this config file and search for Debugfs. Sorry, you should search for kprobe. So kprobe is by, then means it is supported. So this is the first step. So you should, if it is not there, then you should do make menu config, enable the Debugfs, and then only we can proceed with the next step. So now, as the command says, it is mounted in 6 kernel debug. So we can move to that path. Go to sys-kernel debug tracing. So here in this file, you should go to tracing on. So this should be enabled. Only then you can do this. So you can enable disable by using echo command. So this is actually disabling. You can enable back. So here you have to use the trace. Here tracer should be NOP. Only then you can use this debugger. So you have one more video to trace the tracefs file that you can check by where you can change this tracer output. So now we are going to see the output only in this tracer. We'll start. So for that, first initially you should know the code to do this. So what are all the files we need to affect is kprop events. Here you have to update and this will show the output. These are the only two files. You need kprop event as well as kprop profile will be the output. So what to write in this file? So go to the boot prompt here. So you have a system.map file. So this will have all the symbols which are installed in the kernel. So you can use this or you can use this file as well. Okay, all symbols. So this will give all the files which are all the functions which you can do as a probe and you can check. So not all the files can be used. So for example, here I am taking a ping command. So I have identified two different functions. One is ICMP send and the other is ICMP receive. We'll try to trace this. So this is ICMP send. You search that file here. This is the address location, the symbol table. So this. So now to trace this, this should not be a static or inline. So how to confirm it is you have to have a source code here. If you don't have a source code, you can go to the online browser. So this I have added in the blog this link. So this is nothing but the source code browser link. So here you can directly come. You can put that ICMP send. So here you can see it is not a static or inline. So we can do a probe for this. So the second function which I found is ICMP receive. This is not also not a static or inline. So we can probe. So this has a return value that is not having a return value. So even you can grep like this in the system. Okay, like this you can grep to find the address. So you have to write the probe event. So how to write is P is for probe, R is for return value. So what we are going to write is we are going to probe this ICMP send and ICMP receive. So for ICMP send, this is a dummy function which we are writing. So it can be any function. Just to identify debug, I have given debug underscore ICMP. Then what are all the flags you want to print? You can print clone, stack address, register, parent thread ID, child thread ID, plus 4 address like this we are printing. So this is for send, this is for receive. And for receive we also have a return value. So for that we are writing a new probe. So that is having a return value. So all these we are writing inside the kprobe event. So I'll just copy this. I've added this function in the blog. You can take it if required, or you can write your own function. So before that, before writing, if you go to sys kernel debug and probes, here you can find the list of all we have enabled. So we have not enabled anything. So this is a black list. So for these functions, you can never apply a probe. So that's why, because it will send assembly or it will block the kernel or run inside the loop. So that's why they have identified some functions and they have put that here. So you should not try to do probe for this. That's why it is given as a blacklist. So now once we add our variable, this should come to the list. So that is the expectation. So now initially profile is empty, event is also empty. I'll just copy that whatever we have. We send the whatever I have explained is the same thing. So only two are added, the third one is missed. Now, see, it has added all the three probes. One is probe debug ICMP send, and then other one is receive, other one is the return value for the receive. So now if you see the probe profile, so you will have, see, but no hit is there. So that's why we are getting 0, 0. We'll make it hit, then we should be able to get value. Even trace will not have anything because we have not yet started. So to remove any particular variable, for example, I want to remove this. How to remove is we echo hyphen colon and then we should do a problem. So when it is already enabled or running, we cannot do this. So the last variable is removed. The profile is removed. I'll add it back. This is even and this is profile. So now we have added. Now we'll go and see in the list. List was empty. See now all three variables are added. This is the pointer address in the key symbol table. You have to check this. If this is wrong, then you cannot debug. So this is the receive call because for return value, this is for send. So all are disabled. So now we have to enable it. How to enable is, so once you give this command in trace inside event, you will have a kprobe created. So before that it will not be there. So what all traces you have enabled? So you have given three events. So three different files folders will be created. This is the global enable function. This is 0. We have to enable it. So now we'll go and see inside each of the function ICMP receive. So here I am just putting star. So it is not enabled filter. So this is the format and the TID which we want to print. In the output you will get this. You remember what we have written in the file. So it is the same thing. Clone, stack variable, register and everything. We'll see one more send will be the same, but we'll see the receive option. So here this format, here it will print the percentage x from where, from this is from kernel function to this function, and this is the argument. So this will print the argument. So now we will try to run and we can check. Place is there. So as we will see with an example in google.com, I'm just pinging. Go to the trace file. It's not there because we have not enabled. So we have to enable it. So for enabling, go to events, kprobe. In that we have a variable called as enable. So make it 1. Now you can go to logs and we can check whether it is enabled. See, all are enabled. Now we should be able to get the traces. Just give a ping. We have got, this is our probe function. This is the actual probe function. This is the address pointer. C1A, the receiving function. It is the same one. This is the stack address. This is the register. This parent process ID, child ID, read ID. So this is called from IRQ. That is interrupt context. So this is return. Return value is, it returns the value as 0. So this will be very useful. You can add probes wherever you required. So now we will try to do a error message to get and see the output. I'm sending a packet which is not reachable. So these two were the old traces. Now this is the new trace. So now extra we got a send because some unreachable we have to send. So that is why, or unknown. So this is a flag. This is stack start address, register, and all these things. So like this you can enable and debug. So if you want to disable the traces, as I said, now you can even see this profile. This event profile should have hit. So ICMP send has hit only one time, receive has hit 2 times, and return has hit 2 times. So using this command you can check. This log is still the same. Now we need to disable it. As I said already, you can disable it by echo minus. But it will not allow because it is busy. What we have to do? First we have to go to the event kprob enable. So this should become 0 now. And we have to make sure that all the variables inside this is 0. 0. This is also 0. So all are zeros. So now this function should work. So we just copy this variable also. So that is removed. This will do a proper cleanup. So all are deleted now. You can event is null. You should always clean it so that it is not overloaded. So even the events also should be deleted. See, kprobe itself is deleted. So this is the proper cleanup. This is also very useful tool. You can probe the kernel parameters, return value, you can understand. You can even dump all the structures and everything. It's very useful tool. You can use this for debugging. Thank you. This video we will try to see how to capture any Netlink packets. So for that, I'm just creating an interface like this. Creating a dummy interface. Sudo ip link add dum if type dummy. If you see, dummy interface will be created. Sorry, it will create with this dum ifac. So this interface is created, and then I'm just adding an IPv6 address to that. Then I'm renaming this to Ethan. So I just want to find out the flow of this. when I'm renaming this to ETH10. So the steps are, we have to create a netlink first. So what we have to do is use this command ip link add any name you can give. We are going to create a type NL monitor, netlink monitor. So now you see it will create a interface. See, this interface will start capturing the netlink command, but this is down, so we will make it up first. So sudo ip link set dev NL monup. So see, now this interface has come up. So the purpose of this interface, you see, it is IPsec unspec. So it will capture all the, we'll just capture and we'll try to understand, take the packet out and we'll understand. So now I'm going to capture this packet using this tcpdum -i. All the outputs I'm going to capture in the netlink.pkm. So this file I'm doing when I'm executing this command. So when I'm executing this command, what happens? The netlink. Netlink is nothing but the packet from kernel, and so I give an enter. Now it starts capturing. I think it has captured. So it has captured 55 packets. If you see here in this, what has happened is it has deleted this interface, and it has created a new ETH10 interface. Now we will capture the packet. We'll take the packet outside and we will check. So this is the capture netlink packet. So here if you click on protocol, you can find all the protocols packet. See, all are netlink related packets. This is netlink, this is netlink generic. These are all routes. So we have sent packet with respect to route. So all the route netlink packet should come here. So these are the 3 different packets. Now we will just check general packet. So this is general netlink packet. So this is Linux header, generic, and this netlink packet. It just says the end of the thread and it gives the port ID and the date. So this is nothing, not useful for us. This is a generic header. This also does not have any useful data for us. We'll go to the route. So this is netlink route, see, RT netlink. So this is the packet which is sent. So this is length is the one. We get a network interface info. The flag used is this one. Acknowledges dump filter. So this creates the interface that gets the information, and this one creates the interface. You can see the name, device type is loopback, and you can see the device name. So it creates the loopback interface for the device. So all these are for loopback. So this is one more create interface. So this should be for, this is for ENP680. So like that you can capture, see, now we have captured the packet and we are able to see the MTU and everything. If any issue you get in the netlink, you can just capture. See, this is for router docker 0. So this is for the device NL, whatever the interface which we have created. So like that you can check all the route related commands. So we have checked ETH10. So like this, if you check, you can find the ETH10 related information. I'm just showing all the interface things. See, so we have, what we have done here is we have created new interface, right? So it is create new interface, and this interface family, interface device type, what is the if index? The if index is 109, right? So at least we can just check. Capture. So for ETH10, it has given the if index as 109. So now we will check in the node whether it is correct. So you go to this path, sys class net. Inside that, eth10 is created. Now we'll go inside this and we can check. Now it should be 109. So the kernel has given 109, so we have also got 109. We can also check this command with use this command ip link show 109 eth10. Like this also you can check. So this is how you can verify the cross verify this by doing a packet capture. This is a very useful tool. I'll just recap it. Actually, what you have to do is just to create a NLMon type. Mainly the type is NLMon. This can be any name, and just make it up and try to capture the packet. So this will give all the route related Netlink calls. Not only route, generic and all the Netlink calls. If you want to try learn about Netlink, you can just capture the packet and do some actions related to Netlink. Just add route, delete route, and you can capture the packet and try to understand. Thank you. Segment routing using Linux. We are taking a same subnet to configure and try. This is a static segment routing. So I have taken 4 nodes, R1, R2, R3 and R4. They will be running in a Docker 0, Bridge 0 interface. So this is a Linux simulation. If you are not aware about creating a Docker and virtual machines, you can see those in my channel. So now we'll start. Now we are going to create 4 Dockers. So this is a Linux machine. So I have already created the Dockers. So this is the command to create the Docker. So this is the file, and the command to create is this. So I'll just show the Docker file once again. I am taking Ubuntu 22 and all the basic Linux utilities I am installing. That's it. And then if you run this command, the Docker will start. The image will be ready. Actually, these are the Docker images. This is the SRv6 image which is created. So I am going to create an 4 instance of this and start running. So we will start. So this is H1, that is R1 as per the diagram. This is H2, H3, this is R. So now if you go to the host, you can see all the 4 Dockers are running. Docker PS. You see all the 4 Dockers are running. You can see the brctl command. So this shows this is the Docker 0. As per the diagram, this Docker 0 runs all eth1. So all these uses a veth interface. If you see, these are all the veth interfaces which are connected to each other. So now we have to enable v6 also. I have a separate video to enable this. I'll just show you. This is the file. So all the IP addresses will start from FC. FC is a private IP. You can just confirm. So it is confirmed. See, this is 2. This is 3. 4. And this is 5. So now we can directly ping to this 5 from 1 because all are in the same bridge. But if you do like this, it will not send an segment routing packet. You can just confirm. This is pre-dump. This is the sending interface. Just capture any of the interface. So it sends a normal ICM without segment routing header. You can see it is normal ICMP v6 without any of the UDP segment routing header. Sorry, it's not segment UDP. In IPv6 header, 2 headers will be added. That is not added here. So capture the packet. If you see echo request and reply, it has a source and destination directly. So there is no any extra header in IPv6 if you see. So this is the normal way of working with the bridge. Now we are going to convert this using a segment routing. We'll see the configuration. Wording in all the Dockers. So this is the command to enable it. You can see it will be in proc sys net IPv6 config all and forwarding. It should be set to 1. You can configure this in all the 4 Dockers. So it is configured. The next step is in this first node we need to reach to the last 5, this 5th node through segment routing. So what is the IP we have to add is, we have to add this. This means that this is any prefix you can give. This FC0, any prefix you can give. This via is the next hop. This next node connected R2's this IP. So this we have to give, and then we are going to give this route. So what this means is, this is also the 5th route. If you see, this is the R4's IP. This is the R4's IP. We see this one. We are going to reach to that. If we want to reach to that, we have to encapsulate with IP segment 6, and mode is encaps. It will put one packet inside the other, and then what are the segment list next hops to go? This is 100, which we have just previously configured, this one, and then the next where to go we have given, and then we have to give the interface. Interface here is ETH0. So once we give this R show, so this is how we have configured. So this is to reach to the end. So previously it was working, now we are encapsulating it, and we are sending. We are encapsulating with 2 segments. This is the first segment, this is the second segment. So this is the configuration in the first node. So if you see, 2 configurations we have to add. To reach this, we have to use next hop this and this to all the configuration. Then now we will go to R2. R2 we have to, once it goes to R2, it will have the second IP, that is 600, 6000. So that IP will add. What is this 4 is the next hop of this here, R3 side. And then what we have to add is, we have to add an end cap saying that this is the end segment. This is ETH0. So this 10 will be removed from here. IP-6 R. So these are the 2 commands. Then in R3 we have to give it to the IP layer. So to give it to the IP layer, this is the command. Here we get the last command, last one, that is 6006. Sorry, this one, 6006. This will come in the packet. So this we have to strip it and give it to the route 6. So DT6 action. So this is what we are giving here, IP6 R. So this is the command. So now we are done with the configurations. Now we will check whether ping is working. So it is working. This time if we capture the packets, you can see I'll show the detailed packets also, but it is actually encapsulating because the next header is also filled. So we will take all the packets, we have to capture all these packets. So 1, 2, 3, 4, all 4 interfaces we'll capture and we will check the packets. Use brctl show and to find out all the veth interfaces and run this command tcpdump -q v-w pcap. Now ping is already flowing, we can stop and run also. So now we have captured this interface, and then the same way I am putting veth2 to capture here. Each time you can stop or just this same should do. The packet we can check the first node. So this is the request. You see, you will see through you have 2 IPv6 header. One is the outer one, the other one is the inner one. Inner one has the actual source and the actual destination. This is the dummy which has 100 as a next hop list. You can see this here. You will have a segment routing header. This segment routing header. So number of segments left is 1. That means you have one more segment, and then this is the address list through which it has to process. The next process should be 6006. The next place, if you see, this is the second one. So you will have, sorry, not this. No, this is the second one which has 6006. Here you should have segment left is 0. The segment left is 0. So after this, whatever packet you capture, it will not have that. See, it has popped out and it has sent the normal packet. So this is how IPv6 segment routing for v6 with the same subnet. So if you have different subnet, configuration everything will be the same, except that instead of FEC00 you will have a subnet IP. We'll check that in the next video. Thank you. Today we will see how to configure static v6 with Linux with using the different subnet. Last time we saw with the default Docker, now with this a different subnet. So you need to create 3 different bridges like this SRv6. This is actually setup is R1, R2, R3 and R4 are back to back connected. So how do you connect it is, we connect using SRv6 static subnet. We have to create the subnet with 11.1. Here it is 11. This 2 is 12.2 and this is 13. Same way I have configured a IPv6 address also. So for this I am taking R1, R2, R3 and R4 are the routers. This is R1, R2, R3 and R4. So if you see, initially it is all connected with a bridge. So now we have to, this is single bridge. This is a previous video. If you have not seen with the same subnet, you can see that to find the steps to configure. I will start from here. So now we have to remove this from the default bridge. So this is the script I am using to remove. So this should remove all the brctl show, all the div. Now if you go inside the interface, you will not have this eth0. So now it is cleaned up. Now we have to create a Docker network. So we don't have a network. So create a network. I am using this command. This is a driver. I am using a bridge driver. IPv6 I am enabling with this subnet 1 and this. If you see the diagram, it is the same thing. 1.1, the other is 2.2, 2001, other is 3001. So that is how I am configuring. I am giving the name as subnet 1, 2, 3. We just run the script. Network ls. So this should create. So now it has created all the 3 subnets. Still you will not have anything here because you have to connect this with that. So this is the script I am used to connect. So H1 and H2 are connected, as you see. This is R1, this is H1. This is 2 and 3 are connected, 3 and 4 are connected. So we'll just run the script to connect it. Once we run the script, if we come to this, see we have 1001. Here you should have 1001 and 2001. So have 1001 as well. Sorry, 1001 as well as 2001. The other one is you will have 2001 and 2000 and 3000 network. So this should be 3000 network for V6. So now we have to ping to this 3001. So anyway it will not work. Previous configuration it was working. Now we have to make this work. So that is the target now using segment routing. So you can go to the configurations. So in R1, R2 and R3, all the nodes you have to enable IPv6 forwarding. That is the first step. Enable IPv6 forwarding in all the 4 nodes. Yes, we are done. Then in R1 you have to add this route. This is any prefix you can give, and this 1.1001:3 is the next hop of R2. This one. And then we have to give this one. Interface configured is ETH1, right? So I just configure, copy this command. What this command is, 3001 is the last node. You can see the R4 node. R4 node's IP is 3001. So you can use the 3001 segment routing, and this is the first network, the second network, and ETH1. So the first node configuration is done. Now we go to the second node. Second node, so as you see, this is the segment, second segment. So for the second segment we have to add the route to the R3s as the next hop. So there is no command. You can just confirm whether R3 is 2001, 2013. So it's right. So you can configure this here. Then next you have to configure saying that this is the last segment. And we have to give to ETH1. R2 it is done. Now we have to go to R3. R3 we have to pop up. In R3 you will get this IP. So for that IP you have to do the action as giving it to the IPv6 table. That is DT T6 is IPv6 table, and it is segment 6 local. So here also it is local, there also it is local. So now we are done. Now we can check the packets. We can check the ping whether it is working. You have to give -a because it will take a resolve. So you can capture the packet and we can check. You can capture the packet in this node. For this, see you will have 1, 2, 3, 4, 5, 6 interfaces you have to capture and we have to check. You can use TCP dump, TCP. So request and reply is coming. So I will take the packet out of the Wireshark and we can check. Capture the packets in all the 6 bridge interfaces. You can give BRCTL in the host node. You can give BRCTL show, and you can capture on all these bridges. This bridge VETH1 or 1, 2, 3, 4, 5, 6. All the 6 interfaces you can capture. I have already captured. This is the first interface. So if you see, you will have two headers. So this is 1.1, but this is outside is the actual header. This the internal header, which it will have segment 1 and with the next hop. So then this will go to the bridge 2, and bridge 2 should have a different one. See, this is a different subnet, that is 1000, this is 6000. Here you should have segment length as 0. IPv6, this is segments left is 0. And then in the third bridge you should not have anything because it has removed it. So this is how the packet is sent. You can capture in the intermediate node, will also have the same thing. That's why I have not shown it. So this is how you can try IPv6 using a different subnet in Linux. It is very easy. You can understand this. Thank you.